Good morning, everyone. Okay, welcome to 102. Sorry, it was just uh the other session ran a little late. So okay. All right. Have you had a chance to take a look at the Saturday's lecture? I don't know. All right, but what we did on Saturday was it's only like a short session talking about the electric field and electric force calculation. Okay, and I hope that during that session, we were talking about the connections between the force and the electric field. Okay, and the key, I think, maybe is the the point that I would like to emphasize on is just saying that if you know how to calculate the field, you will be able to get the force very easily. And I hope I made it pretty clear that we can do that in that lecture. All right. So I hope you had a chance to take a look at that. All right. But anyway, if not, that is okay because we're going to do again here, except today we are going to do some calculus here. Okay. All right. I hope you
Okay.
like it. With no extra fat. Okay, guys, we have to do this. And we're gonna do just only just okay, not too much. All right, but you have a chance to try this one, and it will be clear that all right, as long as the setup is not super complicated, you will be able to do this. Okay, what happens to the electric field from a continuous charge distribution? When they say continuous charge, think about it like in the past, what we have done was just all right, you have point charge number one, charge number two, charge number three lying around, and then you try to figure out the net electric field from vector summation. But what if the charge come in like a cloud? You have like as you know some crazy piece of charge, and then it's just like look very continuous. So there's no way that you will be able to do it one by one by saying that hey, that's Q1, Q2, Q3 anymore, and that's when you need calculus. The way to do that is just you have to do it yourself. Slice those pieces of charge into a tiny piece first, okay, one by one, and then you assume that within that, maybe in this case, there's three-dimensional space, so it's a cube. So within that cube, it contains a little bit of charge in there, okay, and then that charge will contribute to the electric field at a point of interest. For example, if you are interested in calculating the electric field at point P, for example, then you all you need to ask is just like, hey, John, how far away is that delta Q to the point P? Let's say it's R. And the R hat is still there. I hope by this time you sort of can relate to the R hats a little bit. It's a unit vector pointing in the radial direction. When they say radial direction, it's just the line connecting between the charge generating the fields and the point of calculation. Okay, that's no big deal. So what you have over here is the vector that point along the R. That is your R hat. So I'm asking you, hey guys, what is going to be the charge? I'm sorry, what is going to be the field due to this delta Q charge? And you say, well, Dan, that's no big deal. It's just K times the charge that's generating the field, yeah, divided by the distance square. That is done.
Okay.
Not too bad. Because this field is still like a tiny, tiny field, you probably can say this is just a delta E. It's like a mini field. Okay. So what is the difference? What does it mean by what is the difference? The delta, the delta?
What is the difference between the equation
And the
from
previous one, no difference. It's a
yeah?
Coulomb's law. It's the exact same equation. That's that no difference whatsoever. But the difference is we are interested in just a tiny piece of charge ourselves. We sort of like we slice it. Okay, we just say, hey, take a look at just this portion of the charge. And then what you're going to do is we're just gonna take this to be super, super duper small. And you're gonna call this dq. So that means this cube turned into like an infinitesimally small cube. It turns into like zero size cube, super small. Okay, so this equation would turn into something like now differential. It's like mini E. Now it's a differential of E, like super small electric field. is going to be K dq over R squared. You guys with me now? And then what you need to do is just keep doing this for the rest of the charge. You do the next Q. Oh, okay. I hope. Okay, somewhere. There you go. You do the next one. 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 You do the next. I mean, you just do them all. Just keep doing it. Okay. But the bad thing about this one is, well, oops, sorry. The bad thing about this one is it's not super easy in the sense that here, each one will contribute to the field. Contribute to the field at point E. Contribute to the field at point E. Contribute to the field at point, point P, sorry. Contribute to the field at point P. See? So what you are getting at the end, you're going to get like a crazy amount of DE here, there, 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 on and on. You have to sum all this stuff, everything, until you get to a single final net electric field at point P. That will be your grand solution, I mean, grand answer, grand solution, or whatever. That's sigma E at that point. Cool? No, we're not trying to find the center of mass. This is away from the charge. And we are not talking about the mass whatsoever. This is a charge. But this figure, it's sort of like resonate with whatever you're looking at and the way that we are about to do and things that we're about to, calculate. All right. So you are about to calculate the electric field from continuous charge distribution. So that's why you need calculus plus the summation over here is a vector summation. So this is the reason that why we're going to call this vector calculus, because it's a calculus of vector quantities. Okay. All right. So you sort of agree with me that what the vector calculus is. Well, you will get a taste of this one way or another, but this is like an application of that vector calculus. I think this is a good one. Okay, let's take a look. Say, okay, so don't worry too much. It might look very hard at this point because this is like a general setup for the whole calculation. But in actuality, what we are going to do, it's like simple problems. It's like doable problems, or at least the distribution of the charge is not like super general, right? For example, let's attack this one. Okay, I will call this like a minimum requirement. Everyone need to be able to do this problem. Seriously. Okay, let's take a look at it. You have a rod of length L and has a uniform positive charge per unit length. All right, we'll discuss more on this, what it means, a charge per unit length, lambda, and a total charge Q. Calculate the electric field at a point P located along the axis of the rod and distance A from one end. So according to the figure that's already written there. So that's kind of nice. Okay, so you would like to calculate the electric field at, in this case, they place the point P at the origin and they slide the rod a little bit toward the right. So the left end of the rod is at a distance A, according to the requirements here. So actually, this is the setup that you can, you can have a different setup if you like, but because this already sort of like have a figure accompanying this, so this is good. So let's use this one, and then we're going to calculate based on this configuration here. All right, so point P is at the origin, left ends of the rod is at x equal to A. So the right end of the rod is going to be at A plus L. So that's okay. That's no big deal. All right, guys. How can we find the electric field at point P? First step, you slice this rod into a tiny piece first. That's what we did. There. Okay. And we're going to assume that within this tiny piece, it contains a tiny amount of charge dq. Perfect. So far, so good. All right, we're gonna follow whatever we just set up right here. All right, we gotta do that. So let's imagine what happens to the point P due to this dq charge. Well, that's no big deal. The electric field due to this dq charge probably gonna be super small. Let's call it dE for now. And from the Coulomb's law is gonna be K. The charge that's generating the field, we name it dq. Now, what is going to be the distance from dq to point P, guys? And that's what the setup is for. The setup is already nice. But this is good. You already put everything on an x-axis. So this axis will give you the location perfectly. With me? Wherever you chop or slice this dq piece from the rod, that piece of the charge is already located at x away from point P because you already put point P at the origin. Sounds good? Okay, okay. Very good. So what you have over here is just x squared. So you already put the dE in the form of the coordinate x. Nice. Now you need them all. When you say you need them all means you're going to have to do this on every piece in the rod. So you start slicing from the left end, chop, chop, you get one dq here. You do next, chop, 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 all the way to the right end. You guys with me? But the good thing about the setup that we have here is, look at this. When you are at the left, for example, left end of the rod, you still have the charge dq anyway. It's a differential amount. It's super, super, super infinitesimally small charge. And you can still use the same x because dq is already on the x-axis. So that means this expression right here works everywhere on this rod. Okay? So what you need to do is you just have to sum them up. You have to sum electric field due to each piece on the rod. The left ends of the rod will generate dE over here. When you move on to the next slice, jump, you get another dE here. And then you slice again, jump, you get another dE here. You slice again, jump, you get another dE here. You slice one more, you get another dE. You're going to do it all the way to the right end of the rod. You're going to get a bunch of dE, right? You just need to sum this all together. But because you're going to do this continuously from left end of the rod to the right end of the rod, what you did was integral. With me? Okay. You're going to do summation from x equal to a. That's where you're starting from. That's your left ends of the rod. You slice the first dq there. Bam. You get the first dq at x equal to a. And then you do all the way until x equal to a plus L. Once you're done with this, what you get is the net electric field that you want. That's your setup right here. Cool? Now here comes the main part. How can we figure this out? You cannot do this one just yet because the function that you want to integrate is already in the x variable. That is fine. No problem with that. That's kind of nice. But the integrating variable is still under q. It doesn't go well. Okay, you want them to be on the same variable. So you will be able to do the integration. So how can we convert either from q to x or x to q? What do you think? And this is the key part. Look at this. Every time that you slice a piece of charge and you have the dq charge contained in it, no matter how small it is, it's going to take up some space on the rod. That means you're going to have to take up some width or some length of the rod. Let me name it super, super duper small dx. You got that one? So if you know the length of the rod that you slice out, can you figure out the amount of charge within that slice? Well, Ajahn, no problem. Remember this? charge per length. So the meaning of the charge per length means once you know the length, you multiply by this charge per length, you will get back the charge. If you have 1 meter, that means it's going to be 1 times lambda. You get 1 lambda coulomb in 1 meter. Okay. You have 2 meter, it's going to be 2 lambda. 3 meter, 3 lambda. 5 meter, 5 lambda. Now you have dx meter. How much charge you going to get? Lambda dx. With me?
Okay.
So that's how I can relate the amount of charge and the length of the rod by going through charge per unit length. So that's why actually we can name this lambda to be charge density. Yes. Welcome. Even though it sounds weird, but density usually is like you relate to the volume. Well, but not necessary. The reason is because you don't have volume here. This problem is only single dimension, is one dimensional problem. There's no width, there's no depth. You only have the length. How could we be, you're not going to be able to get the second and the third dimension anyway. So no matter it is, it's going to be the area, it's going to be the length, or it's going to be the pure like total volume. You can name this density, doesn't matter. Okay, like this one, you can name it's like a one-dimensional, 1D. It's one-dimensional charge density. Okay, all right, good. So what you have over here is now I can turn the dq into something of dx. So how our equation will look like now? It's gonna look like lambda dx over x squared, and now you can actually write a to a plus l now because everything is under x. So you don't even have to put x equal to something to signify that, hey, our variable is x right now because everything is in the x forms. Very nice. Whatever constant, I can pull it out. K is constant, lambda is constant. So all you need to do is just to do the integral of 1 over x squared from a to a plus l. And this one, I think you guys can do it because it's just x to the negative 2. The integration will get you to x to the negative 1 with the negative sign in the front. So k lambda is in the front. The integral of that one gives you 1 over x negative. You're going from a to a plus l. You guys with me so far? Not bad, not bad. Almost done, almost done. All right, you substitute the upper limit, subtract out the lower limit because you have the negative sign. So let me do the last one first, and then you do that later. Here we go. And that is done, guys.
Okay.
And this one, you have a choice. They say about you're not going to use Q here. No big deal because this one is sort of like, I mean, information that seems to be overload here. They say that the total charge on this rod is Q. You know the length of the charge is L. So actually, you know that the lambda is going to be Q over L as well. So it depends on what is the final form that you want to write out. You want to write in terms of the Q, or you want to stick with the lambda. That's up to you. That's no big deal. But at the end, that is your net electric field at point P. Isn't that cool?
Okay.
Maybe? No?
No.
All right. Not bad, I hope. All right, this is going to be the first exercise for you guys to see that, okay, well, calculus is, is calculus, but this is the application of the calculus in the topic of electric fields. All right, and now, I mean, this is just an additional question that you can ask. If you would like to place a charge here, oh, let me put like a red one here. What is the force on this charge? I can put like a charge, mini charge Q there. Now it's going to be easy. The force on that charge is going to be Q times E. Done. See? So that's why I said in general, finding the electric field first seems to be a way to go. And then later, if you want to figure out the force, then you can pretty much, go back and multiply the charge that's sitting at the position of the electric field that you already had, then you get the force right away. That's done.
Okay.
Okay, not bad. Want to try yourself? Like, want to give it a shot? The next one? Yeah, all right, guys. Any questions up to this point? Seems doable? Okay. All right, don't worry too much. The question in the exam or problems in the exam will be like around the level that we're going to do together here. All right, it's not going to be like super crazy shape, like, charge distribution, and then you have to figure out like crazy summation of some weird vectors and all this stuff. No. All right, it's going to be like a super highly symmetric setup that you will be able to calculate quite straightforwardly. All right, even though not easily, but it's just very doable. Try next one, guys. All right, this one is cool. All right, we're gonna actually because we're not gonna be able to cover the whole thing, but I mean, from time to time, you might have to see something like this. You have a ring of radius A and carries a uniformly distributed positive total charge Q. So at least now you know that the whole charge in this ring is Q, uniformly distributed. Calculate the electric field due to the ring at a point P lying at distance X from its center along the central axis perpendicular to the plane of the ring. All right, so you have start from the center of the ring, shoot it out perpendicularly from the plane, right, at the distance X away from that center. What is going to be your electric field? Wow. You want to try it first? Give it a shot. And this is going to be fun. No need. All right, I have you think like, 2-minute head starts and see how it goes. But first thing first, you need to slice your piece of charge out into a tiny piece first, of course. And you might want to slice it out. Let's call it, there is a charge dq containing in that tiny piece of charge first. Okay, that's going to be your first step. And you're going to deal with the mini electric field due to that mini charge dq. That's the first thing that you need to do. It looks complicated, but it's not. Okay, very good, very good. I can see some of you already. No, I don't see anything. I'm just kidding. All right. First, that tiny piece of electric field is going to be K, charge generating the field, dq, over the distance. And distance actually is fixed. You know the radius of the ring A, you know the distance from the center of the ring X. So R is just a Pythagorean theorem. So it's going to be square root A squared plus X squared. That's not a big deal at all. So I can say it's going to be R squared. And the R, if you like, is just A squared plus X squared. The square root just disappeared. All right, that is very doable up to this point. But the bad thing about this one is, don't forget, it's the vector. So that means it's going to point along this direction here. Cool? So far, so good. Now, let me show you again what is going to happen if you keep doing this at other locations. For example, if you go to the opposite ends of this, look at the bottom of the ring. You slice another piece of this one, that's another dq there. What happened to this? Well, of course, Ajahn, you're going to get some electric field at point P in this direction here. So let me write it here. With me? However, now it's going to point up a bit here. Right there. But from the look of it, it's going to be the same DE expression. Except now the magnitude, even though looks the same, but it's going to point in the different direction. You guys with me? The reason that the magnitude is going to look the same because it's the same DQ here. It's the same distance R, same. So it's a k dq over r square. The only difference is now is pointing upward a little bit. So if you sort of like get a feeling of what is about to happen, what happened if you look at the front? Let's look at the front. You slice under the piece here. You're gonna get some DQ here. Oh, it looks very ugly here. That's what it is. Okay, there you are. That's what I want. So over here, you will generate electric field pointing in. It's sort of, you have to think like perspectively. It's sort of inward. So the electric field is gonna point sort of like into the page a little bit. And if you do one more, let's do one more. Let's look at the four corner there. If you slice a tiny piece on the back side of this one, you have another DQ there. Then your electric field, of course, is going to come out in the front right here. And you're going to get look in the perspective direction. It's going to go like this. It's look dirty now. Maybe it's just too big. Okay, here you go. All right. But the idea is you have to go around the ring. You have to go around the ring. So it means that you have to just like slide here, slide, everywhere, right? So each DQ on the ring will generate the DE at point P along, I mean, sort of like corresponding to the DQ. But once you complete the whole ring, what you're going to end up at point P, guys? You're going to have like tons of this DE that's actually wrapping around a cone. Here, you guys with me? I hope I draw it. With me? You're going to get a lot of DE on the surface of the cone. Backside too. Okay? What you want is just the net summation of these vectors on the surface of the cone here. How can you do that? Well, John, that's not too bad because it looks very symmetric. Why? I can break this vector into two components. One component is perpendicular to the x-axis, and the other component will be along the x-axis. You guys with me? So if I go around the surface of the cone, I'm going to get the perpendicular component. So the perpendicular component will fill up the circle that is perpendicular to the x-axis. You guys with me? And these components eventually will have its pair pointing in opposite direction in all directions. So what you get is just going to be perfect cancellation of this component.
Okay.
Cool. So that means what you have to sum is just the x components of each DE. That's what you need to sum up. So that means I don't have to care about the perpendicular components. I only need to care the x component, and then I'll just do head to tail, and then just sum them all up. So what I need is the DE along the x-axis. You guys with me? That is the calculus part of your, that is the vector part of your calculus. You have to take into account the directions of the quantity that you need to sum. And this is our analysis. Say, okay, I only need the x components of this. So what is the x component of this? You take the original DE and you only take just the component along the x. So if you're going to name this angle to be theta, so this is going to be your DE cosine theta. You guys with me now? Yeah, the sine component, you just throw them away because you know that you're going to get perfect cancellation on that side, on that perpendicular direction. You only care about the cosine part of this one. So it's going to be cosine theta. Cool. All right. And this cosine theta is known actually because if you look at the right triangle that you have over here that you define the theta. Oh, whoa, whoa, whoa. Define the theta right there. Cosine theta is just the adjacent over hypotenuse. So cosine theta over here is just going to be x over r. That's a known value and it's fixed. So not much to be done here. Just keep going. So it's going to be k dq over r squared times x over r. Okay. And then you'd want them all, but then sum them up. Take them all. I'm going to take them all. I'm just going to do complete the whole cycle. So I'm going to take them all, d equals sine, d equals sine, d equals sine, sum them up. Now you start to wonder about how can we do this integral? How can we find net integral of this? All right, calm down. It's not that bad. Pull out the constants from me first. What are those constants? Okay, k is out. What else I can pull out from the integral? X, no, x is fixed. X is out. What else? R is fixed. R can be out. There are 3 r's now, so it's r cubed. So what you have left is just the integral of the dq. This is the reason why you don't need to do that sort of geometrical integration or anything, because what is the integral of dq, guys? You just take the dq, oops, sorry, dq, and sum them up, or the whole ring. You're going to get back the charge of the ring. Whew. That's nice.
Okay.
U over R Q. Done. Complete.
Okay.
Not bad. Not bad at all. Or maybe it's already bad. You guys still with me? I don't know. You look so quiet. It's been quiet. Is it doable? I'm there. Well, isn't it fun? All right. I mean, first time seeing this looks very complicated for everyone, I'm sure. But I hope that, I mean, throughout the calculation, it's not getting worse. It's getting better over the course of solving this problem. Okay. All right. Let's do one more, shall we? And then we can take a break. Okay. All right. The complications is due to the vector properties of the field. That's why it make things like to another level. You need to worry about the directions. If these were to be just like a scalar quantities that you will face later when you deal with the potential, it's going to be, it seems to be a lot easier. All right. But for now, all right, once you deal with the field, it's a vector quantity, so cannot avoid it. All right, let's do one more, guys. Last one. All right, and we can complete this handout. All right, this is gonna be the upper limit of the question that you can sort of like estimate, or you can imagine that you're gonna face. All right, I'm not gonna put any harder question than this one. All right, the figure shows a plastic rod having a uniformly distributed charge Q and it's negative. All right, so let me stress on that one, is a negative charge. The rod has been bent in a 20-degree angle to 20-degree circular arc of radius r. So that's good. So it's 1/3 of a circle. Okay. And it's already been centered at the origin, and then the arc is sitting nicely, symmetrically above and below the x-axis. So that's very good. In terms of Q and R, what is the electric field due to the rod at point P? That's what you want. All right, this is going to be the hardest one, guys, but I want you to try this one first. Let's set things up just like what we did. All right, we have done 2 of them already. This one won't be any difference. It will look exactly the same, except toward the end, maybe a difference, but setting up must be the same. All right, guys, give it a shot. Kidding. All right, let's set things up here and see, can you have a setup that looks like what I'm about to do for you guys? All right, don't be afraid. Just anything, just write it down. It will get better over time. Not bad. What do you think? All right. It's like completely quiet. I don't know. All right. First, you slice this into a tiny piece of charge. Okay. And let me say, just like before, there must be a charge dq contained in it. All right. Now, because this is a negative charge, electric field will point towards it. Yes. So let me draw that here. Electric field gonna point towards it. So let me draw like a big one here. There you go. So that's the direction of the electric field generated by this dq right here. How much? Well, John, that's not bad. Let me name this dE for now. So my dE is going to be K. The charge generating the field is dQ. Okay. Over the distance from the origin to the ring to the arc is R square. Cool. Yes, yes, yes. Cool. That's not bad, but it's a vector, of course. So it's the R hats. Yeah, nice. But then you think, okay, Atan, it will happen at other points. Starting from the top, you slide all the way to the bottom. So each one will generate its own dE. So let me give you an example of this one at the top. It's right there. Okay. And let's go down to the bottom. You're going to go down here. Okay. So that means along the way, you're going to get a bunch of this dE everywhere, here and there, 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 there. Okay. All the way down to the bottom. Down. Okay. All right. I have to finish this one just to make it clear. There you go. It's supposed to look nicer than this. All right. It's going to trace. It's supposed to trace along with this. Okay, so my arrow doesn't touch. That's kind of bad. Oh no. Why did I do this? Okay. All right, let me trace that arc first. So it's gonna go all the way down here. Here we go. There you go. There you go. All right, but you see what I'm trying to get to here. Okay, here we go. All right. So you're supposed to draw a nicer one than mine. Okay, here we go. So you're gonna get this, you're gonna get that dE, 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 a lot of dE, a lot of dE, a lot. All right, let me just put on top of that O1. There you go. All right, here we go. So these are all the dE that generated from the arc. All I need is the summation of these bunch of these vectors right here. So again, from the look of this one, Bajan, you have a symmetry here in play. You have you have equal amount of vector above the x-axis and below the x-axis. That's nice. When I say nice, because look at the blue. I can split this blue into two components again. You can do the vertical components and you can do the horizontal component here. With me? So that's where the blue can be split into two components. And if you look at the opposite ends of this one, the one that's opposite to the blue is the red one down here. Okay, I'm just put on. Okay, let me do like a thicker one here. So it would just go above everything else. Here we go. All right. So look at the red. I can do the same thing with the red. I can split them into vertical components and horizontal components. Same thing right there. With me? And it's perfect. The vertical components will cancel themselves out because of the symmetry. And this will happen on any page, or I mean, everywhere on this arc right here. You have the same amount of vector on top and on the bottom. So I mean, top and bottom always cancel out in the vertical components. So once again, this problem showing that all you need to sum is just the x components of the electric field. Okay, with me, guys? So x component is the only component that you need to sum. You can throw away the y components. I don't care. Okay. So what's next is now I only care about the x component of this. And it comes from the original dE. And now is your turn to figure out what should be your theta. All right. So look at the blue. If I say, okay, John, let me name this theta, because the theta has to be your variable. Even though you know the starting point of the theta is going to be 60 degrees, but you're starting, I mean, somewhere, and then you have to sweep down. Okay, so the theta will change, and then sweep out every value of the angle theta. Okay, so I would say cosine theta. Very good. Just like before. All right, there's a question comes in. Can I just roughly say that the electric field will point towards A? Yeah, roughly, you know. Yeah. I mean, yeah. But then if this is the exam problem, then you're probably gonna roughly get some points. Like if you, okay, this is like a 10 points problems, and then you say, okay, roughly point along the x, then you might get like roughly about 1 point out of 10. Okay, back to our business over here. Now I put dE cosine theta. That's all I need. So I just plug in the value of the dE is a k dq over r squared and cosine theta. You want them all. So you want to start integrating this whole thing. Sum them up. From the theta at the top, which is at 60 degrees, that's where you're starting the first cut right here. That's your first cut. And you do all the way to the theta equal to negative 60. The reason I use negative 60 because now you go below, I mean, you go sort of like, you know, opposite to the one that's going upward there. So that's your last cut right here down here. Yeah, that's the first cut right there. And this is your last cut right here at the negative 60. Once you get that, that is your net electric field along the x-axis, and that will be your final electric field as well. All right, it looks complicated. Hey, but hey, you're almost done. What's constant can we pull out? Can you see? K is out. Actually, R squared is also out. Now you're facing the same problem again. Your variable right now is theta, but your integrating variable is Q. How can you turn that into theta? Once again, come back to our business over here. dq right here must be linked to the size of the cut that you slice out from the arc. Okay, slowly here. All right, the hardest part is going to be here. No matter how small this is, it will take up some distance here. Let me name this ds, sort of like an arc length or something. Okay, so if that arc length is ds, charge over here is going to be equal to lambda ds. You remember the lambda, our friends here?
Okay.
Okay, our lambda is charge per length. So now because your length is ds, the amount of charge in this length is going to be lambda ds. But then, John, ds is still not the theta, it's the arc length. But then you say, okay, that's not a big deal because if you remember the definition of the theta and the arc length over here is linked through the radius. You say that the theta is just the S over R. That's by definition of the theta or the angle is the arc length over radius. So when you have something super, super small in here, your theta turns into d theta. That's super small. Your S turns into ds. So no big deal. It's still the same relationship anyway. So that means your ds is just the RD theta. So that's lambda RD theta. And that's what you need to replace integrating variable theta. Well, it's not as a function in terms of the integrating variable theta. So now integral, it looks like dq is a lambda RD theta cosine theta. See, perfect. So now everything is already under theta. Theta goes from 60 to negative 60. Actually, all right, I'll comment about where should I start, where should I stop a little bit later. But for now, let's do natural like this, but it's completely opposite to what it's supposed to be. But just for now, okay. So what you have here is whatever constant can be pulled out. Let me pull out the constant here. So lambda is constant, R is also constant. So I can pull lambda out. I can pull R out. K is still there in the front. All you need to integrate is integrate cosine theta d theta. See?
Okay.
Can you see the condition? Everyone knows how to integrate the cosine theta now. It's a sine theta, and you substitute the upper limit, lower limit. So I mean, your answer is already waiting for you. Now, what about the comments that I just said? There was a problem, even though you tend to say, hey, I want to go from top to the bottom. But every time you put the limits of integration, you want to go from the lower to the upper, right? That's usually the case. So actually the starting point is supposed to be the one that actually lowest. But then when you say lowest, it means, does it mean lowest geometrically? Lowest mean the lower ends of the rod? No. The angle, every time you talk about the angle, you go right hand rule, right hand. Your angle is measured counterclockwise. Yeah, that's why this is a negative 60 degree and this one is positive 60 degree because you want to go counterclockwise. And because you said at x-axis, this is when it's 0 degree. So to be correct in terms of the sign, you're supposed to start your integration from negative 60 to positive 60. That's what it is. I mean, usually you want to go from low to high in your integration all the time. So that's why you're going to go negative to positive. All right. So that's the way it goes. Even though you say about that is a summation anyway, but well, not totally true because what we're doing is the vector calculus. So when you do the vector calculus, or I mean, in general, the calculus stuff, when you do the lower limit, it must mean lower and the upper limit mean upper if you want to get the sign correctly at the end. Okay. So what I'm doing is going to go from negative 60 to positive 60. That's the sign will be fine. But if you go opposite, your final result will have a negative sign. That's all. But that's not too bad, but it's just going to get the incorrect directions of the final results. Okay, here we go. So what do you have left? Okay, let me move this out a bit. Okay, this definition seems to be okay. Right there. I could put it there here. Okay. Squeeze down. All right. Okay, good. So what you have here is now is just the integral of cosine. Now I just cancel one R out. Integral of cosine is sine. And it just substitute the lower limits and upper limits. And that's it. Sine 60 is √3 over 2. Sine negative 60 is another negative √3 over 2. When you subtract them out, you get twice of that. So at the end, it's √3 lambda K over R. And that's it. Done, guys.
Okay.
Point to your right along the positive x-axis with the magnitude of √3 lambda K over R. Woo. Okay. I think that is it for vector calculus in electric field. No more. This is the last exercise that I want you to try. All right. So, I mean, you might have to go back and then try it yourself again. But I hope by going through these three problems together, you can see that it's not that bad. I hope. All right. We'll have a chance to go back to do this kind of thing one more time, but with a different setup in that later, you don't need to worry about the directions anymore. But the calculus is still here. Right. And then we can do this one more time and you can see the similarity and the difference later. Okay, sounds good. There's a question coming, how this will help me building particle as you will see this different kind of integration. That's what I'm saying. If you want to do the accelerator, definitely you cannot get away with the calculus, because in that accelerator, magnetic field, electric field, everything will go crazy and you have to solve differential equation. So yeah, you cannot get away with it. All right, it's going to be more complicated than this. Let's say 1000x. All right, guys, take a break at this point and then we'll sort of go through the next handout, okay, after the break, okay? All right, guys, see you in a bit. Let's say meet back at 11:10, sounds good? All right, guys, see you in a bit. This first. All right, so now we're going to move on to the next concepts that equally important to the field, and this one is called electric potential. Whoa. Okay. All right. So what we are about to say is, what does it mean by electric potential? I don't know how much you're familiar with these concepts, but you must have heard of gravitational potential. And I will tell you right out, they are the same thing. Seriously.
Okay.
All right. So what we are doing right now is the same concept as the gravitational potential. So I will show you the analogy between the two. And by sort of like using the analogy, I would say that you will understand this right away.
Okay.
Maybe not, but anyway, it's going to be good. All right. So we're going to talk about the electric potential energy. That's going to look very, very similar to the gravitational potential energy. And finally, all right, toward the end of this, we'll talk about the electric fields and potential relationship, and that probably be next lecture. So the key of this today's lecture is going to be, how can you determine the electric potential and what it is? Okay, let's dive into it. It turns out, if you think back during the day of doing Newtonian physics and all this stuff, you had a lot of applications that can be solved using energy, right? So many problems, you use energy analysis, and then you can solve this and that. It's the same thing here. We're going to use the concepts of energy because now we have the fundamental force to be electric force. It's going to be exactly the same thing as the fundamental force back in the day of the gravitational force. So if we are able to build a gravitational energy, we will be able to build electric potential energy right here. Now the problem is, how much have you heard of the definition of the potential back in the day of the gravity? And here is the one that we need to talk. All right, maybe there's so many words here in this slide and all this stuff, but the key is we'll come back to touch on these points on the way forward here. But the key is we want to define this potential energy properly. Right? What does it mean? So take a look at this. And this definitely, I guarantee you, is going to be confusing for sure. All right. But stick with me a little bit. And I hope by the end of this, it will be clear. I don't know. This is tough. All right. I don't like this either. It's kind of annoying at first. But once you get a hang of it, it's not too bad. All right. Imagine this. You have a field pointing down. When I say you have a field, now in your head, you can think of this to be G. Gravity. Why not? It's the same field, the same kind of field. Okay. Now, you have a ball at point A. You can think of the mass. But now, if I want to make the analogy with the charge, with the electric, I would say you have a charge Q right here. See, you see the similarity between the two? Now you let the ball go. It would drop down to point B. And actually, you can even say, hey, at point A, I have mgh at A, and at point B is mgh at B. potential energy due to gravity. You should have the same thing here for the electric potential energy. See, because think about it. If you have a charge Q at point A and you let it go, it will travel down, given that Q is positive, of course. It will travel down due to, there must be a QE force acting on this and pull this charge downward. So that means by doing that, if you want the energy perspective of this whole thing, it would say that you're starting from some energy of the charge Q, and then eventually the charge Q travel along the electric field to a new position with a new potential. But you said before, back in the day, that point A in the gravity has a higher potential because it's higher. You should say the same thing with the electric field, because starting from A, Q is higher than the B. With me now?
Okay.
See? So that means as long as you're going along the field, you are going in the direction of lower potential energy. Okay? And the better thing is this, because you can make the analogy with the electric, mass is equivalent to the charge, G is equivalent to the E, and H is probably equivalent to the distance or whatever. So you should be able to expect that the formula for the electric potential energy is going to be QED. And the answer is yes.
Okay.
But we're gonna go a little bit deeper. I mean, we're gonna go like, super sound like authentic stuff here. So the way that you determine the energy change, you have to do a little bit of work. And we already learned from thermodynamics that the work is just the energy transfer, correct? So let's imagine opposite case, just to make things a little bit sort of like, a little bit dramatic here. So you're starting from low point B. You want to drag, now let's forget about the mass now. We want to focus on the electric field now. So let me erase all the M here. All right, so you won't get confused here. All right, so now I'm going to start from point B. I want to bring the charge from point B back to A. What do you need to do, guys? Well, then of course, if you want to take back the charge, you have to supply some force to it. Very good. And because you can do whatever you like, you can pull it up, you can do acceleration, you can do quick pull, quick, slow pull, smooth pull, whatever. But eventually the amount of work that you're going to give it to this charge from B to A will be all the same. So why don't do something simple? Let's do an equilibrium move. So means let's apply the external force to be exactly the same force that this charge is experiencing, QE. Why not? Let's do a simple one. Yeah. Okay. So we're going to do that. I'm going to drag this charge in like equilibrium state from point B to point A. How much work I'm doing? Of course, Ajahn, the work that you are doing is going to be the W is, okay, let me zoom it out first. The amount of charge that you are doing is going to be F dot delta S. And let me call this the W external, because that's what I am doing. Okay. So, actually, just to make it neat, let me use the color coded here. So I'm going to use blue color here. So work done due to my force is going to be F dot the delta S. Force times the distance along the direction of the force. And in this case, you can see is D. That's all right. All right. It's going to be FD. That's good. So far, so good. All right. The reason I can say it's FD because, all right, the displacement is going to be up as well. So as you can see, the force that I'm applying is in the same direction as my displacement. So that's why I get the positive work done. I get a positive work done because I am the one pulling this charge up. That's me. But then because you do it in a sort of like an equilibrium manner, and you would like to express this charge from the perspective of the field. You guys with me now? F is just external force acting on this. But because you know that the F is going to be opposite to the QE, so I can actually replace this F with the negative QE because I'm doing against the field. With me now? Okay, cool. So far so good. So what you have over here is you're going to get a negative sign in the front because you know every time you refer to the field, the external force will be opposite to this field. To do what? To increase the potential. Delta U is positive. You guys with me? By pulling this charge up, I'm pulling it up. Oh, this is sort of like, there you go. I'm pulling it up. I am increasing its potential energy. But this up is opposite to the field. The field is down. So that is the reason why we need a negative sign, because when you do the positive change in energy, you have to do it against the field, or that is going to be the negative work done from the W due to the external force. You guys with me now? It looks confusing in a little bit, but this is what happening here is because, well, okay, this line may be confused to you. Sorry, maybe this is my bad. The delta U equal to negative dW over here. It means that it's the negative W due to the field. So that just to make clear. All right. Otherwise, then you guys will get confused. Sorry, my bad. This is bad. Okay, this is a W external. Here we go. All right. And what you have over here is the negative of that. So, well, I don't like this. Actually, you can actually forget about this. Maybe this one get more confused by having this one on. Okay, here you go. So, and oh, actually, okay, this is me. This is my typo right here. Shoot. All right, that's why it looks confusing. Okay, guys, I'm sorry. You're supposed to have a negative sign right here, starting from here, because F is the negative QE. That's why this is the missing part. All right, that's my bad. Okay, that's better. All right, guys, sorry. Just forget about this. And you just say the work done by the external force from thermodynamics, if you like, is just the change in the internal energy, right? But right now, I mean, there's no internal energy in this case because you are looking at a system that has potential energy at this point. We're not talking about the kinetic energy or anything. So the concept is the work done is the energy transfer. Because I am doing some work that is an external work, supply the energy to the system. At the end result, you get positive change. You get positive change in the energy. You guys with me now? Energy change is up. How much up? Same amount, this much. So in conclusion, sorry for the confusion, all right, about the sign here. So in conclusion, to increase the energy of the system, you have to do the work done against the fields. That's why there is a negative sign there. That's my whole point right there.
Okay.
Okay. So I think maybe the most confusing part that people seem to sort of like don't like it so much is because of this negative sign here. All right. So that's why I want to confirm to you that the negative sign here is just coming from the common sense of every time you have a mass, you want to increase the potential energy, you have to pull it up like this, right? You are going against the field right now. Every time you go against the field, you are going in the direction of increasing the energy, potential energy. It's going to have to be exactly the same here. So if you have the electric field pointing down, you going against the field, that's the increasing direction of the potential energy. Same thing with the gravity. Okay, against the gravity, that's you increase the potential energy. You go along the potential, you go along with the field, you're going downward in energy. Okay, cool.
Okay.
All right. So, and that gives you the grand conclusion of this one right here. You can figure out the change of the potential energy from point to point by doing the negative Q times E dot S. That's what it is. even though I write it as a calculus-based expression, but that's all right. The concept is there. My key point to take here is where the negative sign is from. It's from our definition. We say that mass fall from high to low is going from high potential to a lower potential. So that's what we agree, that we want to call something of higher position to be higher in potential as well. So that's why field pointing from high to low. So that means if you want to go to a higher place where the potential energy is higher, you have to go against the field, and hence that negative sign right there. Woo. All right.
Okay.
I don't know, maybe taking too much time, but that's 15 minutes of explanation. I don't know if it's too much or not. Now, here's the kicker. We have some extra stuff for you for the electric stuff. In potential, in the gravitational potential, you don't have this. We have this for electric. The reason is because of this. It's my guess, but I think that's because the utilization is there. When you are looking at the mass, M, this mass is with you. You can look at this mass wherever it goes. And the problem in Newtonian physics, stick with this mass. You do something with the mass, you throw the mass, you look at the momentum of the mass, you're doing the energy change of the mass. Everything is about the mass. Mass is huge. It's a macroscopic stuff. You can deal with it easily. But not for the electrons, not for the protons, not for the ion in solution or whatever. So those stuff cannot, you can track it, but that's going to be super hard. And if you go down to the business of working with the electrons, actually all of electrons in this universe considered to be indistinguishable. You are not possible to tag an electron. You cannot label an electron, hey, I'm going to call you my electron 01, and the next one I'm going to call you my electron number 02. No, you cannot. So that means you don't have any ability to, hey, I'm interested in this charge, and then I'm going to follow this charge along wherever it goes. You go into the wire or go out into the space. No, you cannot. So that's why in general, you don't want to define the potential energy for the whole lump sum of the charge. You guys with me? That's my idea. So you probably want to do something sort of like intrinsic to those. So you don't want to attach to the amount of charge that you are considering. So that's why we define, here we go. Welcome. Electric. You probably look at this like, what? Yeah, the only thing that's missing from it is the word energy. It is, I know, it's a bad definition of the name and all this stuff. But anyway, that's what it is. We stick with it. So you drop the word energy, you are down with the electric potential. And the definition of the electric potential is just the energy per unit charge. And in the textbook, they probably just talk about this unit charge to be like a test charge. So every time you read this test charge in the textbook and all this stuff, don't worry. You think of it like 1 coulomb. You turn it into 1. That means it's per unit charge. Units, it's 1. So that's good. So that means the stuff that you do over here, you will do equally well by talking about what is going on per unit charge. So you're just going to move this Q to the left-hand side. So if you do that, delta U between any two spots per unit charge, you're going to call it potential energy. And because this is the change, you're going to call it the potential energy change. I'm sorry, the potential energy change, yeah, per unit charge. I'm sorry. There we go. You're going to call it the energy change per unit charge turns into potential change. Yeah, drop the energy. It's just the change in the potential. And this is potential difference. Yeah, that's what it is. So potential difference is just energy change, but think of it per unit charge. Okay, so back in here, so all you need to do now, you can define the potential difference by looking at the change of the energy per unit charge. So it means you drop that charge, you get this expression. The nice thing about this one is, can you see something here in this expression? Charge is not involved anymore. So the good thing about this expression is You only need to know the field. Once you get to the field, you can pretty much explain the potential right away without having anything in this play, whatever, in this space whatsoever. That's the nice thing about this. Okay. So it's just like right now, you have gravitational field. And you don't need to put any mass in it. You will be able to tell the higher point has a higher potential. But back in the day, you don't know what to call this thing, but you know the higher has a more potential energy, right? But you say if you want to use the energy, you have to place the mass there to be able to figure out the energy. But then once you define the potential, you don't need the mass there. All you know is just like this is very intuitive. You know the higher point has a higher potential, the lower point has a lower potential. So actually, use the word potential is not that bad, I think. All right, the units of this, because it's the energy is joule, per charge is coulomb, joule per coulomb is the volt that you're so familiar with. And now I hope you understand why we use the units volt in our household. Because, for example, if you use the 5-volt charger, for example, so your adapter that supply 5 volts means the potential difference is 5 volts. Now it depends on how much, charge that you want to move through that 5 volts. If you move it through that 5 volt with the 1 coulomb, you're using the energy of 5 joule. If you move through that 5 volt with the 10 coulomb, you use 50 joule. You move through that one 1,000 coulombs, you use 5,000 joules. See? So by knowing the potential difference, you will be able to trace back to the amount of energy that you're using by just multiply back the charge. Isn't that nice? Okay, so from here, I think I can give you like a grand summary of the stuff that you probably just have to face. We introduce the force along with the field. These two comes very sort of like in pair by just saying that you have the field multiplied by the charge, you get back the force. Same thing over here. We define the energy, potential energy, and then you do it per unit charge. You call it the potential without the energy. You want to get back to the potential energy, multiply back the charge. Isn't that cool?
Okay.
And these are the I think that's all you need. F, E, U, and V. Done. Okay. All right. So, to us now, you only need 2. I think E and V is already good enough. Okay. Once you know E and V, you can go back to F and U anytime you like. All right. So I hope this gives you an overview what is supposed to be happening. In conclusion, for this slide here, if you want, and in this slide is for those of you that still sort of don't get the concepts of the field and the potential so well, use this slide to compare with the mass and the gravitational field one more time. That might help you. Okay. All right, guys, let me ask you this question. I don't know you understand this by how much. I don't know how much you absorb this whole material yet, but let's answer this one. Now here comes the thing. Unlike gravity, is always pointing down. The electric field can point in any direction. So let's test it. Guys, I have an electric field point from left to right. Now, if I know that point A is to the left of point B and C, but B and C are at the same distance, vertical distance, let's say. Okay, from point A, and the separation is D right here. What is the potential difference from A to B? That's my question. Okay, one more time. From A to C, along the field directions, the distance from A to C is D. Now I want to go from A to B. With the distance along the field is the same, but A to B is a diagonal. All right, so it's take longer distance to get to the B, but at the end, it ends up at the separation, if you measure perpendicularly from the field, to be the same value, D. What is the potential difference from A to B? The reason I'm asking this because everyone should be able to answer the potential difference between A and C now. Okay, let's give it a shot. All right, there is one coming. All right, 0. All right, we'll see. All right, here we go. Let me ask you this. What is the potential difference from A to C? Think logically. A and C, which one has a higher potential? So you have to say, when you go along the fields, you're going in the direction of lower potential. So this is high, this is low. This might help if you turn your head sideways and make the E point downward from point of view. What you have over here is A is higher than C. Does that make sense? Yeah, okay, that's good, that's good, that's good. All right, so definitely A is higher than C. But then the thing is that I want to show you is this. Back in the day of the gravity, if your lower the bottom of the screen is the ground level, I can bring this mass up to the upper level of the screen. Everyone know this is the potential difference, the potential energy difference, mgh. But I can also do this. I can bring this mass to the corner of this screen, or I can stop at any position on the top of my screen. As long as I'm staying at the same level, you guys will say that the mass has a potential of mgh. Is that correct?
Okay.
Do you see what I'm getting at right now? So if you turn your head sideways and take a look at it, you should have the same scenario over here that Bojan, wait a second. If I draw a line here, perpendicular to the field, that should be my level too. So that means as long as I'm sticking with this line here, no matter where I am on this line, I am at the same potential. Yes, with me? Try again. If I draw another line down here, perpendicular to the field, cut through the field perpendicularly, as long as I'm sticking with this level, I should have the same potential too. You guys with me now? So that's my whole point. The point is, whenever you have an electric field that looks uniform like this, you make the analogy to the gravity. You cut through this, it will give you potential level. Believe it or not, that's what it is. So that means the potential difference from A to B has to be exactly the same as the potential difference from A to C. And to be even more general, I can go from anywhere to anywhere here, anywhere to anywhere there. It will give me exactly the same potential difference. With me now?
Okay.
So that's the idea. You can always cut the field perpendicularly to get to the potential. And as long as you keep cutting those electric fields, those cuts will connect into a line. And that line will give you the line that's showing you the same potential value. Isn't that cool? All right, now I want to show you quantitatively how can you get back to that conclusion by using definition that we sort of introduced. We already said, if you want to figure out the potential difference between 2 points, you do E dot ds with the negative sign. Cool, everyone with me?
Okay.
Okay, just take the field dot with the displacements. Okay, now look at the A and B, even though it's point diagonally, but the field is point horizontally. So what you have over here is, okay, let me write it on the side. It's gonna be E times ds cosine theta. You guys with me? Remember the dot product, A dot B is the magnitude of A times magnitude of B, cosine of the angle between the two vectors. E is horizontal. ds is just the mini vector pointing along the S. So the angle between the ds and the E is going to be theta. So it's going to be ds cosine theta. And right now, because E is constant, I can pull it out. And the ds cosine theta, cosine theta is also fixed. It's a fixed angle. I just have the integral of the ds left. But what is the integral of the ds? You just take the ds and sum them up, sum them up, sum them up, sum them up, sum them up. At the end, you're going to get the whole S coming out. So this is just S. So it's just negative ES cosine theta. See, it's the same result as this one. But what is the DS cosine theta, guys? S cosine theta is back to the D. This is the S cosine theta. So it's a negative ED, and that's it.
Okay.
So no matter where I go, I can go to crazy angle, whatever angle. At the end, the component of the distance that I need is just the distance along the direction of the field. This is by definition of the dot product. Okay, that's why I don't care. As long as the separation is D, I can jump from the yellow line to the blue line. The potential difference are all the same.
Okay.
Cool? I don't know you can't call this cool. And I don't know I talked too much today, but that's what I tried, sort of like try to explain to you what is behind the scenes that might give you confusions in the future. So I'll just give you confusion now. All right. Okay. And this will spring you to answering what will be the potential from a point charge, believe it or not. All right. But I don't want to go through this calculus stuff anymore. But I'll just give you like a qualitative analysis of this one. So I hope this will resonate well with what we have learned so far. I don't care so much about derivation of this, but the idea is this. Now, just bear with me a bit here. I will show you this and I hope it makes sense to you. Here, now you have a point charge Q. Everyone now understand now from the field's perspective that it will generate electric field all over the place around this charge, everywhere. It goes everywhere. No problem. And because if this is a positive charge, the field will point outward. That is fine. That is perfectly fine. Now I'm going to cut through this field line perpendicularly, guys. What do you get? You're going to end up with a sphere. I'm going to cut this, cut this, cut this perpendicular. So now you see that every time that I give a cut and I take those cuts, connect them into, in this case, it's three-dimensional, you get a surface. So you get a sphere. Yes, with me? So on this sphere, you can sit anywhere you like on this sphere. You are going to get the same potential. With me now? From the cut of the electric field line. If you move to another position on the field, you do the cut again. You're going to come up with another sphere. But that sphere will have a different size of the first one. And that is another potential energy or potential. Can you see what I'm getting at now? So this whole thing is just like, this is just like, you can imagine Q as the earth. And now your radius is just the elevation that you are away from the earth surface. Yeah, makes sense? But now it's like you're zooming out. When you do like a gravity pointing down, it's like you're already on the surface of the earth. But once you fly out into the space and you look back at the earth, everything now actually is a sphere. So over here, it means if you start from one level, you can stay at any point on this sphere, you sharing the same potential, or in parentheses, potential energy. And then if you want to move to the other radius, you will jump to a new value of the potential. And then you can go in any path you like. You can go like this, you can go like that, you can go crazy here and end up with that. Doesn't matter. The only thing that is changed is going to happen when you change the R, the radius. But the initial point and the final point, that's all you care about. You don't care about the path. And that's bring us back to this one that we skipped in the first place. The concept of the potential is so convenient to use because it's independence of path. I start my mass down here. I can pull it up straight. That's MGH. I can pull wiggling and whatever I want, zigzag, it's MGH. I can throw it outside and throw it back in here, that's MGH. I can stop anywhere I like on this level, it's all MGH. It's path independence. You only need to care about where is your starting point, where's your final point. And this is the reason why you only care about the distance from the charge. And here comes the potential from a charge, a point charge. You can calculate it to be KQ over R. All right, derivation, you can just leave it there. Don't worry about it. Okay, guys? Sort of weak so far?
Okay.
All right. And you're probably wondering about John, you keep saying that you always calculate the potential difference. Why you end up with just potential? Usually it's kind of like doesn't make sense. This expression turns out to be is V minus V infinity, guys. You assume that if you are so far away from the charge, you won't feel any potential from this charge at all. So you say that V at infinite distance is going to be 0. And that's how you define potential from a point charge. Sounds good?
Okay.
This is the conclusion over here. You have two ways of getting to the potential. If it's a point charge, you do this formula right here, KQ over R. But if you have the information about the field, you use this expression right here to figure out what is going to be the potential difference within that field. Okay? And this is how we're going to turn our attention to the field and the potential. And if you want to get back to the force and the energy, all you need to do is just what charge you are talking about. Just multiply back. You can get everything you like. Okay, so our main focus will be on this and this now. It's more convenient to use. That's all. Okay, sounds cool? Alrighty. Here, there's a question in higher level physics. Electron is just a wave function. All right, we can discuss later. You talk about wave function now. That's not going to be electromagnetic theory at this point. Okay, guys. So this slide will give you like a grand conclusion of what I have just talked about. Right? Potential to be 0. It's independence. We can name it conservative force, on and on if you like. And the closed loop will get you back potential, on and on. All right. You can read it through, but we can learn better with examples later. All right. So I hope this will give you like wow, it's just I talk for the whole period. Sorry. But by doing this next time on Wednesday, I will show you examples over examples, and then we can finish this handout very easily on Wednesday. And that will allow us to get to the connections to the next topic that needs the concept of potential. And then we can use that for some applications in capacitors and capacitance. All right. And that will be another kind of fun stuff. All right. There will be a bunch of calculus built into this module right here, guys. Guarantee, with no extra charge.
Okay.
All right, guys. Yes. All right. And I hope this is not too bad. And let it sink in for a couple of days. I'll see you on Wednesday, and I will go through a lot of exercises. Sounds good? All right, guys. Thank you for sticking around. I'll see you guys on Wednesday. All right. Bye-bye.
Okay.